In this video, we're going to take a look at an introduction to proof by induction. Now, proof by induction is an extremely important tool that we have as a method of proof. And similar to, say, proof by contradiction and how we can use that to prove certain results, the same is true for proof by induction. So for a proof by induction, we follow 4 key steps here. So what's the first step in a proof by induction? Well, we have the basis step. So here we prove that the statement is true, that n equals 1. Now, it's important to note here that it doesn't have to be n equals 1. So it could be, for example, n equals 2, n equals 3, and in certain cases, you might not even be able to use n equals 1. There might be a restriction on n that prevents you using n equals 1. However, as a general rule, choosing n equals 1 is a good starting point. Okay, so that's step 1, nice and straightforward. Step 2 then, we have the assumption step, and again, this is pretty straightforward. We just assume that the general statement is true for n equals k. So this is important now, step 2, because it helps us massively with step 3. So what do we have here for step 3? Well, we have the inductive step. So now what we're going to do is show that the statement is true for n equals k plus 1. And this is often the part where students struggle the most because this often involves a lot of algebraic manipulation. And if your algebraic skills aren't quite up to scratch, you might struggle at first with this. However, once you see quite a few questions based on proof by induction, you'll see that these questions often follow quite a similar pattern. And it's not too bad once you've done, like I said, quite a few of these questions. However, at first you might find this a little bit challenging. Okay, so step 3, the most important part of our proof by induction, and like I said, often where the most challenging algebraic manipulation is involved. And then finally, once we've completed step 3, we have the final step, step 4, which is the conclusion. So we now have a general statement then that this is true for all positive integers. Okay, so like I said, just the 4 steps there, and kind of just looking at those 4 steps written down isn't the most intuitive. So what we're going to do now is just take a look at 2 practice questions here for using proof by induction to prove summation results. So let's get started then with the practice questions. Starting off with question 1 here, then we want to prove using mathematical induction that for n being a positive integer value, the summation of r from 1 to n is equal to a half n times n plus 1. Now, hopefully you recognize this result here. This is a standard result, and this is the summation then of the first n natural numbers. So we can actually prove this result here using mathematical induction or proof by induction. So what's the first step here? Well, we have the basis step. So for the basis step here, in this case, we start by letting n equal 1. So there's no restriction on n here other than that n is a positive integer value. If I let n equal 1 here, what I want to show then is that the left-hand side here is equal to the right-hand side. So on the left-hand side here, what would we get? Well, this is the summation then of r from r equals 1 to 1. Okay, so just replacing n here with 1. And that would simply be equal to 1. Okay, so nice and straightforward there. For the right-hand side here then, what I'm going to do now is replace n here with 1. So I want to get half times 1. And now times this here by 1 plus 1, which is 2. So what I've got here is a half times 1, which is a half, times that by 2, and I simply get 1 there. Okay. And what we can see then is that this is true for n equals 1 because the left-hand side is equal to the right-hand side. So therefore we can say it's true for n equals 1. And then in brackets, I'm going to say that the left-hand side is equal to the right-hand side. Okay. And there we have it. So that's the basis step complete there. So now moving on to step 2 here, which is my assumption step. Let's write this out in full. So for the assumption here, what we're going to do now is assume this is true for n equals k. So assume true. So assume true for n equals k. So if this is true for n equals k, what would we get here? So all I'm going to do is go back to the original equation here. So the sum of r from 1 to n being equal to a half n times n plus 1. I'm just going to replace any n's here now with k. So what I'm going to get here then is the summation of r from r equals 1 to k. And that's equal to a half n. But remember, we just replace n here with k. So I get a half k times by k plus 1. Like so. So we've assumed this is true now for n equals k. So we can't do anything further now with the assumption. But what we're going to do now is use the assumption here to help us with step 3, which is our inductive step. So now moving on to the inductive step here. What do we have now? Well, what we're going to do now is let n equal to k plus 1. So we let n be equal to k plus 1. So here now, if we go back to the original summation here, we have the summation of r from r equals 1. So we originally had n, but now we're replacing n here with k plus 1. So from 1 to k plus 1. Now for this summation here, like we said, we're going to use the assumption step here now to help us with the inductive step. So let me just underline the inductive step here. And how can I use this step here? Step 2, the assumption step, to help us with the inductive step. Well, we know that the summation then of r from 1 to k is equal to this. So in this case then, what I can do is take the summation from 1 to k and then add on the final term, because that would give me the summation then from 1 to k plus 1. Like we said, we've got the summation here of r from 1 to k. The summation of r from r equals 1 k. So that's this assumption here. And then my final term here would just be replacing r with k plus 1. So I simply get plus k plus 1. Okay. Now we know what the summation of r here is. So from r equals 1 to k, for the summation of r, we said that that's equal to a half k times k plus 1. So underneath here, we get half k times k plus 1. And don't forget the final k plus 1 here, so plus k plus 1. Okay. Now, before we go any further here, what's very useful to do when you're working through a proof by induction question is to actually work out what you need at the end. And the way that we do that is just replace n here on the right-hand side with k plus 1. So what we need here, I need a half times k plus 1. So a half k plus 1. And then just replace n here with k plus 1. So it's going to be k plus 1 plus 1. So that would be k plus 2. So that's what we need here at the very end. So at this point here, it's starting to look like we're on the right path, but there's still a bit of work here, a bit of algebraic manipulation to go. So let me just take this up to the top here. What can I do next here? Well, what I'm going to do next here is factor out the k plus 1. So if I factor out the k plus 1 here, I get k plus 1. So k plus 1. Now I times this here by a half k. So I factor out the k plus 1 here, so I get a half k plus 1. Okay, so a half k plus 1 there. And again, we can see that it's starting to look pretty similar, but we're still a little bit off here. So what do I need to do next? Well, I notice we've got a half times k plus 1 times k plus 2. I've got the k plus 1, but I don't have this half out here in front. And I don't have k plus 2. But what I notice then is if I factor out a half here from this second bracket, essentially I times this bracket by 2, and then I can factor out the half in front. So that might look a little bit unusual, but this is quite a common technique when working through these proof by induction questions, especially for the summation results like this. So like I said, I'm going to factor the half out here from this bracket. So essentially I need to times everything inside the bracket by 2 to account for the factor of a half. So we get a half in front. So I get a half here times k plus 1. Then here, like I said, I'm going to double everything inside the bracket. So that'd be a half k doubled, so that'd be k. Then double 1, we get 2. So I get k plus 2 there. Okay. And notice now, this is exactly what we need here. So I've got a half k plus 1, k plus 2. That's what we need. And now I've got the exact same thing here. So as required. So as required here, that's what I was looking for. You don't need to put as required, but I like to just do it here just to kind of show that I've got to the stage that I needed to get to. So now the inductive step here is complete. we now just need to arrive at step 4 here, which is the conclusion. So finally then for the conclusion here, which we can briefly kind of summarize underneath conclusion. So what are we looking to say here? Well, we know that it's true for n equals 1. We proved that here in the basis step. So as this is true, so as true for n equals 1. And if it's true for n equals k, so, and if true for n equals k, then this must be true for n equals k plus 1. Then is true for n equals k plus 1. Okay. And in this case then, this is almost like a domino effect then. So as it's true for n equals 1, and if it's true for n equals k, then this must be true for n equals k plus 1. And almost like a domino effect then, this must be true for all n are positive integers. Okay, so therefore we can say this is true for all n that belong to the positive integers. Okay. And there we have it. So like you can see, we've got the 4 steps here. I've got my basis step, I've got my assumption step, I've got my inductive step, and then the conclusion. And like you can see here, like I said, the inductive step is often the most challenging part to prove by induction. Usually involves the most algebraic manipulation and get it into the required form. But like I said, a good tip here is to basically see what you need to get at the very end, and then you can easily see what you need to arrive at. Okay, like we did here. So that gives the solution there to question 1. So let's take a look now at one more question here for proof by induction. So if we work through one more example here then, so this is question 2. We want to prove using mathematical induction that for n being a positive integer value again, that the summation of r times r plus 1 from 1 to n is equal to a third n times n plus 1 times n plus 2. So starting off with the first step then, our proof by induction. This is the basis step here. So for the basis step here then, in this case, the only restriction on n is that it's a positive integer value. I'm going to let n equal 1. So on the left-hand side here then, what I've got then is the summation here of r times r plus 1 from 1 to 1. Okay, so this is the summation then of r times r plus 1 from r equals 1 to 1. So in other words, I'd just replace r here with 1. So it'd be 1 times 1 plus 1. So in other words, 1 times 2, giving me 2 there. Okay, so the left-hand side here is equal to 2. Let's do the same now for the right-hand side. So for the right-hand side here then, we get a third times n, which is 1. So I'm going to get a third times 1. But then times that by 1 plus 1, which is 2. And we times this here by n plus 2, where n again is 1. So 1 plus 2 is 3. So here I've got 1 times 2, which is 2. Times that by 3, I get 6. And 6 times a third would give me 2 there. Okay. So that basically proves the basis case here. So when we let n equal 1, the left-hand side is equal to the right-hand side. So therefore it's true for n equals 1. So true for n equals 1. Again, the left-hand side is equal to the right-hand side. Okay, so that's the basis step complete. We now move on to the assumption step here. So for the assumption here, we're going to assume that this is true. Assume true for n equals k. Okay, so if we assume that this is true for n equals k, what I'm going to do here now is just replace any n's here with k. Okay, I've got the summation from r equals 1. But it's normally n, but remember n is equal to k now. Well, that's what we're assuming is true anyway. So from 1 to k of r times r plus 1. And that is equal then to a third k. I've got n plus 1 here, so that's going to be k plus 1, and that would be k plus 2. I've got a third k times k plus 1 times k plus 2. Okay. So that's my assumption step complete. We can't do anything further with that. Now we move on to step 3 here, the inductive step. Okay. So now for the inductive step here, we're going to let n equal k plus 1. So let n equal k plus 1 here. Now, if n is equal to k plus 1, then my summation here is going to go from 1 to k plus 1. So r is equal to 1. And this is up to k plus 1 for r times r plus 1. And just like we did for the previous question here, I'm going to simplify this summation as being the sum then from r equals 1 to k, because we've assumed this here for my assumption. That's what we've got for the assumption, I should say. So summation then of r times r plus 1 from r equals 1 to k. And then we're going to add on the last term here in this summation. Okay. And that's when n is equal to k plus 1. That's my last term here, or the k plus 1 term, if that makes sense. So that would be k plus 1 times k plus 1 plus 1. That's going to be plus k plus 1 times k plus 2. Okay, so that makes it clear what I've just done there. So now we know that this summation here, well, if we're assuming true for n equals k, then this summation here is equal to a third k times k plus 1 times k plus 2. Okay, so if I just replace this here then, what I get is a third k times by k plus 1 times by k plus 2. And don't forget the plus k plus 1 times k plus 2. Like so. Now from here, before I go any further, what I'm going to do is just consider what we actually want to get at the very end. So we need, and what we need here, we can find that by replacing n here with k plus 1. I'm going to get a third k plus 1. I've got n plus 1 here, so if n is k plus 1, that's k plus 1 plus 1, so that's k plus 2. And then this final bracket here, n plus 2, that would be k plus 1 plus 2, so that would be k plus 3. What we're looking to do now is take this here and algebraically manipulate this into this form here. Okay. So if we go to the top here to complete this. So what I notice here is I can factor a k plus 1 times k plus 2 out. I'm going to get k plus 1 and k plus 2 on the outside here, like so. So inside now, what I'm going to get here, do this in square brackets, I'm going to get a third k plus 1. So I'm going to get a third k plus 1. And from here now, you might be able to see what's going to happen here. Very similar to the previous question. So I notice here I've got k plus 1 times k plus 2. What we need is a third k plus 1, k plus 2, and k plus 3. So we're pretty close. We need a third here in front, and we need the k plus 3. And again, what I can see is I've got a third k plus 1. So again, what I'm going to do here now is factor the basically 1 over 3 out from this final bracket here. Okay. Obviously, what I need to do then is times everything inside the bracket by 3 to account for a third that we've factored out. I get a third in front. So a third times k plus 1 times k plus 2. And then, like I said here, just times in everything inside this bracket here by 3. So a third k times by 3 would give me k. And then 1 times by 3 would give me plus 3 there. Okay. And notice now we've got exactly what we need here. So a third k plus 1 times k plus 2 times k plus 3. That's exactly what we've got there. So now the inductive step here is complete. And then finally, we just need to give a conclusion here. So now we need a conclusion. So for the conclusion now, as we did for the previous question, we now just need to kind of run through each step. So as this was true for n equals 1, so as true for n equals 1, and if this was true for n equals k as we assumed here, let's just make a note of that here. So and if true for n equals k, then this must be true for n equals k plus 1. So then true, and true for n equals k plus 1. And as a result of that, the domino effect here is that this must be true for all n belonging to the positive integers. So therefore, this is true for all n that belongs to the positive integers. Okay. And there we have it. That's our conclusion complete. We've got our 4 steps there: the basis step, the assumption, the inductive step, and then finally the conclusion. Okay. And there we have it. So that gives us the solution there to the very last example, which was question 2. That brings the end of this video on an introduction to proof by induction.